I'm going to introduce my next speaker. This is Grover Swartzlander. I know. Good friend of mine. I've known him for a while. He's Associate Professor of Imaging Science at Rochester Institute of Technology. His topic of interest is physics and optics, and he's come up with some very interesting ideas about controlling mechanisms for solar sails. And Grover?
Thanks, Andy. It's nice to be here. Thanks for being here after lunch. I hope I don't put you to sleep. My background is in optical tweezers and advanced concepts and very large space telescopes and a variety of other things in nonlinear optics. But I'm very intrigued with this process, and I'm very happy to see some folks here that I've read their books and papers, and now I get a chance to meet them face to face. So my reason for being here is to basically learn and ask questions and hopefully participate after our talks today. So I want to discuss a new type of sail. I believe I haven't seen it discussed in the literature, and it's basically a way of replacing reflective sails with transparent sail. And transparent, you can imagine, well, how the hell are you going to get any momentum on that thing? And well, it's going to be diffractive, so it could be non-absorbing. You could have no conductivity issues to deal with heating, so this already mitigates your thermal management problem. But the other thing is that diffractives, I'm the editor-in-chief for the Journal of the Optical Society of America, Part B, which deals with a lot of optical physics. And there's a whole revolution that's been happening over the last decade or so with metamaterials. And the metamaterials are very broadly defined. The ones I'm really speaking about today are subwave-like diffraction type of gratings that can be controlled electro-optically. So you can imagine you have some structure that produces a single order of diffracted light, and that you can control the direction of that diffracted light. It could either be binary. It could either go to the right or to the left as the light is incident upon that. And that brings a lot of navigational control issues that may be of great advantage for manipulating a solar sail through space. So I show a picture of JFK here. I believe he said that a rising tide lifts all ships, and I think that all boats, and thank you. And so we could think of an analogy here where I'm not talking about interstellar here, but I am talking about a concept that maybe will help us get solar sails off the ground and into space and to start demonstrating them. And I couldn't resist a picture of Natalie Wood. Okay. So again, the idea is to replace reflective sails with diffractive sails. We all know how beautiful diffraction gratings are, and this might look really quite beautiful as it whizzes by the Earth as it sails off into space. Okay, so I'm a physics professor. I like to lecture and have some equations, so I'm going to discuss a little bit about the basic ideas of momentum transfer, the grating equation, efficiency bubbles for forced trajectories, a simple Earth to Mars transfer orbit, and some new ideas I have now. This was published. Some new ideas I have about actually even putting these in very low Earth orbit, mitigating the effects of atmospheric drag, and then finally, what I think is the very first experimental report of radiation pressure on a diffraction grating. Okay, so the basic idea is, many of you know with reflective sail is you have light coming in, you change the attitude of your reflective surface here, light gets reflected because of the law of reflection, and you have a force normal to the grating, normal to the mirror or reflective surface. For a diffraction grating, it's different. You have the grating equation, which says that light can come in at some angle. It can be transmitted. You could also have a reflective case, and I'll discuss both reflective and transmissive gratings, but I think the transmissive grating is more compelling. You can have the light transmitted through the grating, and the force now is not necessarily perpendicular to the surface of your sail. It can be at any arbitrary angle you design. And this gives rise to some really great possibilities. For example, you could have a very large force tangential to the grating instead of normal to the grating. Normal to the surface of the sail, it could be tangential. And you need tangential forces in order to orbit rays, and that's one of the advantages of diffraction gratings. What is more, you can imagine arrays of diffractive materials which you could control electro-optically. So now you have a whole array of digitally controlled sections of your sail that you can navigate for torque, for control and orientation, and correcting various disturbances. Okay, so this all gets down to Maxwell's equations. Perhaps you're familiar with Gauss's law here, which basically sets all the conditions we really need along the surface of a reflective or refractive material. And basically what it says is that you need continuity of the electric field incident on the grating here should be equal to should be continuous. The tangential component should be continuous for the light coming in, and either the light transmitted or the light reflected from that surface. And this gives rise to all kinds of fantastic things, like why the frequency of light is the same coming in and out, if you're going at low velocities, of course. So basically, you match the boundary conditions, or you really do phase matching. And you match the phase across the surface here, and so for reflective surfaces, you end up with the law of reflection. And here, it's a negative because of the way I've assigned my angles here. For grating, you have a component of the k vector. This is the wave vector, if you like, of the light coming into the grating here, which is, of course, proportional to momentum by a factor of h bar. So you have the incident light coming in. The tangential component of that to the surface should be equal to the tangential component of the light coming out, plus something called the grating momentum. Now, many of us who have maybe taken physics and optics classes have heard about the grating momentum, and it's been kind of like kind of an abstract quantity. No one's really actually measure the grating momentum, to my knowledge. But it is there, and it is real, and we can impart momentum onto this grating if it's light enough to see. So anyhow, this boundary condition gives rise to the gradient equation, which tells us that we actually have an order number m, basically, if you like, a correction to either Snell's law or to the law of reflection, includes for a gradient this additional component, which can be very large, actually, if m is a large number. Typically here for advanced subwavelength diffraction grating, m might be 1, and this gradient period lambda is subwavelength. Okay. So this allows usually only a single diffraction order, and that's actually good because you don't want to have a lot of competing orders in your system. So I've looked at 4 different cases: the law of reflection, for a litro grating in reflection mode. So a litro grating is one where you have the grating is here in reflection. The light would come in this way, and for litro reflection, it would be retro-reflected right back. Okay, so that's one case. A litro transmission grating, the light comes in this way, but it gets transmitted down at the equal and opposite angle. So I looked at those 2 cases, and I looked at the gradient at normal incidence and compared these. And these are the force bubbles or the efficiency bubbles you get for this. I'll only point out one particular case here. For the blue case here is for a mirror, law of reflection. And what it shows is that the transverse component or the efficiency is less than 1 because you have to rotate your entire sail by some angle. And as Sandy showed, other people usually assume it's like about 35 degrees. That reduces the efficiency from the theoretical value of 1 down to about 70%. It turns out that, though, for normally incident diffraction grating, you can achieve the full 100% transverse force, theoretically expected force on the grating, with, of course, many caveats and assumptions. But you have there an additional 30% of power there, or force, to accelerate things much faster and get places much quicker. So that's the kind of idea here, and I'll show this again here in this particular case here. What I assert is that a large transverse force is required for orbit raising or orbit lowering. There's a 30% greater theoretical limit for a grating compared to a mirror. So this blue case is the mirror, and the red case is a theoretical value for a diffraction grating. And this assumes that the light comes in at one angle, let's say normal to the grating, and gets diffracted at 90 degrees, okay? Which you can actually achieve. In fact, it can even be eternally reflected inside of the grating and leak out of the grating. It could be a guided mode. But let's just say if you don't want quite that much, if you're happy to be satisfied for like about a 30% decrease, so we get about this 70 some percent of efficiency in a transverse direction. You can now imagine, actually, for a diffraction grating, you could flip from the plus value to the minus value and back and forth using electro-optic control, okay? So electro-optic control says, well, you can have any value between plus and minus 70% if you have a bunch of little tiles of diffraction gradients that you're controlling individually. So it gives you a great amount of control over this orbit raising and the steering of your, or the navigation of your sail, all while staying basically facing the sun or facing your laser source, facing whatever the light source is. Okay? So the idea about this normal grading is that you're always facing the sun. You're not losing any power by having to cock it at 35 degrees. You're always facing the sun. You're collecting 100% of the possible light. Okay, so that's the idea there. All right, so I did a very simple, I'm not a rocket scientist or a trajectorist or anything. I'm just a simple guy running some rugged cutter codes, but I did try to look at what happens if the orientation of a reflective sail compared to a diffraction sail was at a fixed orientation with respect to the sun line, and who would get there first, depending on the lightness of the sail. And it shows, but it showed that is marginally faster every time for a diffractive sail versus a reflective sail, and this. Where we're getting, times on the order of 1.5 years. So this is not we're not talking about light speeds, but what I'd like to know is how to optimize this even better if we end up changing the orientation of the reflector, or we end up changing the component of the diffraction vector. How can we get there even faster? So that's some work in progress. Okay, so that was work that I already published. I wanted to do something new for this conference, so I asked, what happens if we have like a CubeSat compatible Sailcraft? Can we end up putting it in very low Earth orbits? So say, for example, orbit rays from 200 kilometers above the Earth. What we know there is we have a lot of atmospheric drag, and so I didn't know anything about drag, so I kind of went into literature and tried to ask what happens there. Most models show that the atmospheric drag should just be a scale as the velocity squared of your craft going through that atmosphere. So I compared a reflective sail and a diffractive sail. And what you can just see from this cartoon is that you might expect that there's a lot of effective atmosphere buffeting this reflective sail, whereas if the diffractive sail is oriented edgewise, there's essentially no drag on that at all. It's going to be basically governed by what surface drag you have across here. So you can get very low drag, keeping this thing always facing or orbiting with the Earth, and then controlling your force vector electro-optically again. Okay? So this I haven't done an orbital analysis yet of this, but this is yet to be done. But what I did want to ask is how much force would I need, how much radiation pressure would I need to overcome the drag. And so I went back into literature and found some early work on what the coefficient of drag is. I don't know if you can see this. The drag goes as the area times this coefficient of drag, and it goes as velocity squared. So I'm assuming this model, and what it shows is that if you have either an edge-on, let's compare an edge-on sheet versus a sheet that's face-on, so this would be your reflective sail, for example, versus a diffractive sail, you can get like 40 times difference in the coefficient of drag. So this 40 times difference is more the order of magnitude, gives you a lot of advantage for a diffractive sail potentially. So I just wanted to ask, well, what does this actually look like? What does the order of magnitude of drag difference look like? And this shows us two Runge-Kutta codes with basically just a constant drag, but different by a factor of 10. So for a small drag, it stays pretty much in orbit. A factor of 10 basically dumps you out of orbit within just a few cycles. So a factor of 10 is a big deal. Okay, so I looked at I went back. I think I saw a 1950-something paper that gave tabulated values for the atmospheric density. I kind of did a exponential fit to that and try to ask what would really happen in a real atmosphere around the Earth. And what it shows is, in a nutshell, is that if you have a reflective sail, in order to overcome the atmospheric drag, you'd have to put it at least, assuming that you have 1.5 kilowatts per square meter of sunlight, you'd have to launch it at least at about 300 kilometers above the Earth. Whereas for a diffractive sail, because of that lower coefficient of drag and because of and taking into account the even stronger atmosphere in the lower Earth orbit, you could get down to almost 200 kilometers. Now, this assumes whatever the space weather was in 1950-something, and we know things can vary quite a bit, but it's a good model, and it makes a point, is that, well, a sail, thank you very much, a sail that is facing the Earth and being navigated around could potentially mitigate a lot of drag, assuming that drag is well represented by this model. Okay, so the idea, again, an edge-on diffractive sail can be launched to a lower attitude than a reflective sail. And so the question then is, if you can do that, you can get very cheap. You can send hundreds of CubeSats. Lots of students, lots of people, for various reasons, want to send things up into space, and it's obviously quite expensive. So the idea is that you provide a cheap mission to go into a very low Earth orbit. You can either stay stable in a low Earth orbit using a diffractive sail, or you could orbit raised up to GEO, maybe even do an escape velocity. Okay, so the question then is, well, is this real? Okay, so I constructed a torsion oscillator. This is a whole nother story, a lot of fun. And we put a diffractive patch on one side. I bought a diffraction grating from a grating company. This is probably about maybe about 1.5 millimeters thick. And I have friends in Rochester who know how to shave off down to about 200 microns. I had a 200 micron thick diffraction grating. It was a grating that was designed for very high efficiency at single order, and we stuck this into our system. Well, we had a very high vacuum system. I'll show you that system in a second. We had a 25 micron filament, tungsten filament here, and a 1.5 watt laser that some kid had in his basement. Okay, I'll tell you that story in a second. So we basically then reflected a small tracking laser onto the pivot point, and we measured it just as you expect. And voila, we turn the laser on, and bang, 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 the thing starts oscillating as you expect. And we can fit that to a step function response of a harmonic oscillator. It fits very well. From that, we were able to extract the force on the diffractive grating, and we got about 400 piconewtons, which is, what do you, it's a little small thing, come on. Okay. Okay, this thing is less than a centimeter square. Okay, I didn't say it. Okay. And then we were able to measure it, which was really, really fantastic. Okay, so anyhow, grating momentum is real. Okay, so in summary, diffractive sails offer potential advantages over reflective sails, not in all conditions, but not for all trajectories and cases, but certainly for some. They have more favorable efficiencies in theory. They provide electro-optic control, which I think is going to really give a lot of benefits. There may be disadvantages, but you need a transparent conductor, but these can be graphene. These can be, people typically use things like ITO. So there's lots of transparent conductors you could have. These things, people have made these subwave diffraction gratings as thin as 80 nanometers, so they can have very low aerial density. So the real question, I think, is broadband. How broadband can you make it? And is it going to be, typically they can design these things for about 100 nanometer bandwidth right now. So, and they're not trying to do solar sails, they're trying to do other things with them. So future work real quick. No, let me go to this first. This is my team. This is a high school student who built a science project in his lab with the help of his dad. His dad bought him a $6,000 vacuum system. And so we went down there and used one of his 1.5 watt blue lasers. And this is my student, Lucy. She's my graduate student. We drove down there and brought our stuff down. And the reason why we had to do it in the basement is because our floor and our building just shook way too much. And it turns out that a basement floor in Delaware is about the best place you can go for stability. Okay, so the future work is to do optimized studies, look at broadband designs, ask can you really make these things space hardened, which is a huge problem, of course, and see if we can do, how thin can we make these things, including with the transparent conductors. Thank you very much.
I have a question about the broadband design. If you have a large sail and the blue light hitting it is being reflected, say, at 30 degrees, or transmitted at 30 degrees, and the red light is being transmitted at 50 degrees, are you going to be putting in a deforming force with different mechanical stresses at different parts of the sail?
So for a single patch of that grading, you would have, I think you would average over, you'd have to do an integration over all the wavelengths to find out what the force is. But the entire structure would be transmitting it at all those different wavelengths, so that it's going to be an average effect.
Okay, thank you.
Yeah, thanks.
This meeting is about interstellar travel, and the use of sails for interstellar is either as a sundiver mission or as a laser-driven sail. And the bottom line there when selecting sail material is basically absorbance is going to be the limiting factor. So can you give us some feel for what the absorbance of these materials are? How much power can you put on them until they melt?
Right.
And that will ultimately determine whether they have any application for interstellar application.
Yeah. As far as I know, fused silica has a much lower absorbance than any metallic grading. If you talk about dielectric stacks, the dielectric stacks, you may have problems because there's going to be Fabry-Perot resonances inside that stack, which gives you effectively higher absorptance. But there still tend to be oxides, so it may be similar to any oxide, but certainly much better than any metallic. I mean, orders and orders of magnitude better than any metallic sail. These are transparent. And I apologize for not talking about interstellar, but if you came in late, I was hoping that a little sail here will end up helping us to raise sails into the future out into the distant stars.
In one of your slides, you showed a comparison between two sails, and I assume they were the same size sails.
Same aerial density.
Right. But I was wondering, a comparison that we use in system studies more is to see how much mass we could save to drive the same payload. So let's say we had just out of a 5 kilogram payload, how much smaller could we make the sail with a diffractive sail versus a reflective sail?
Okay, so the easy answer is it would be about 30% savings if you're at one of these these nice theoretical values, but it really depends on the trajectory. What is the force model that's going to get you there, and then you can answer that question much more precisely. And it could be more, it could be less than 30%.
Yeah. Maybe I wasn't paying attention. There's something that I didn't understand. If you're hitting a diffraction grating that's flat on, there should be two lobes to the reflection pattern. How do you choose one lobe over the other lobe in order to get force in one direction instead of the other?
That's a good question. So this is the way these sub-wavelength diffraction gratings are designed. They're, if the sub-wavelength, there's often like a super period associated with that, so it could be almost like a sawtooth at the super period, or effectively, usually there's an effective refractive index of these grating structures, sub-wavelength diffraction structures. So think of it as a sawtooth grading, and then you can understand that, it comes in normal, it's going to get a high diffraction efficiency into a single direction.
So the sawtooth will have a blaze angle
Blaze,
that picks one direction over the other. But that won't work when you go all the way to the 90-degree angle, I would assume.
If it's face on 90 degrees, you can certainly get that. People do that in order to couple into waveguides, for example.
Oh, okay. Interesting. Thank you.
You mentioned bandwidth. For Starshot, we're going to see Doppler shifts up to about 20%. Will this effect work over bandwidth that broad? Diffraction gratings usually do have pretty high bandwidth, but I don't know about this technique.
Well, this raises a good question. I'm thinking about it. I've talked to Sandy about this, organizing a small workshop to ask these type of questions. I don't make these gratings. There's a lot of people at very good schools with lots of money that do. And if they knew about this problem, they could answer that question. And 20% probably is not crazy type of bandwidth.
Well, the ones that exist, what kind of bandwidth do they have? You could just measure it.
I said like about 100 nanometers right now.
Yeah, that's a wavelength, not a bandwidth.
100 nanometers divided by, let's say, 800. Okay.
By what?
By 800.
By 800.
Yeah.
1/8, 12%.
Yeah.
Okay.